I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts and cosmic mysteries rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if time itself has softened. Because tonight, we aren't simply exploring space, we're exploring time. The fourth dimension that flows around us, through us, carrying us forward into an unknown future. We're drifting through the science of time travel, a concept that sits at the boundary between fantasy and physics, between impossibility and inevitability. Some of what you hear tonight may surprise you, or at the very least spark some curiosity as you drift off to sleep. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here, too. One sleepy soul at a time. Now, let's begin. Time is the fourth dimension of our universe. We live in a world of three spatial dimensions: up and down, left and right, forward and backward. But there is another dimension woven through everything: time. Unlike the spatial dimensions we can move through freely, time seems to flow in only one direction, carrying us relentlessly from past to future. We cannot step backward through time the way we step backward through space, or can we? Einstein showed us that time is not separate from space but intertwined with it, forming a single fabric called spacetime. Every event that has ever happened or will ever happen exists as a point in this four-dimensional structure. When you move through space, you also move through time. They are inseparable, two aspects of the same cosmic tapestry. Time is not the rigid, universal clock we once believed it to be. Time can stretch and compress. Einstein's theory of special relativity, published in 1905, revealed something extraordinary. Time is not absolute. It does not tick at the same rate for everyone, everywhere. Instead, time is relative. It depends on how fast you're moving and where you are in a gravitational field. Two people can experience time passing at different rates, and both are correct. This is not an illusion or a trick of perception. It is a fundamental property of the universe. If you were to travel at a significant fraction of the speed of light, time would literally slow down for you compared to someone standing still. This effect is called time dilation, and it is real, measurable, and has been proven countless times. The faster you move through space, the slower you move through time. Imagine two twins. One stays on Earth while the other travels into space on a rocket moving at 90% the speed of light. From Earth's perspective, the journey takes 10 years. But for the twin on the ESA rocket, because of time dilation, only about 4.5 years pass. When the traveling twin returns, she is younger than her sibling who stayed home. This is the famous twin paradox, though there is no actual paradox. It is simply how time works in our universe. The traveling twin has moved through time at a different rate. She has, in effect, traveled into the future. This is not science fiction. This is established physics, confirmed by experiment and observation. Time travel to the future is not only possible, it happens all the time. Astronauts aboard the International Space Station are traveling into the future right now. They orbit Earth at about 28,000 kilometers per hour, and although the effect is tiny, time moves slightly slower for them than for people on the ground. When they return to Earth after months in space, they have aged a fraction of a second less than everyone else. They have traveled into the future, if only by a minuscule amount. The effect is real and measurable with atomic clocks. Every astronaut who has ever been to space has time traveled, even if just by milliseconds. Even your GPS navigation system accounts for time dilation. The satellites that provide your location orbit Earth at high speeds and experience weaker gravity than you do on the surface. Both effects cause time to run differently for the satellites than for you. If these relativistic effects were not corrected, your GPS would drift by several kilometers each day. The fact that your phone can pinpoint your location to within meters is proof that Einstein was right. Time dilation is not a theory waiting to be proven. It is the foundation of technology you use every day. Gravity slows time down. Einstein's general theory of relativity, published in 1915, revealed an even stranger truth. Gravity is not just a force pulling objects together. It is the curvature of spacetime itself. Massive objects, like planets and stars, warp the fabric of spacetime around them, creating what we experience as gravity. And in these curved regions, time flows differently. The stronger the gravitational field, the slower time passes. If you stand at sea level, time moves slightly slower for you than for someone at the top of a mountain, because you are deeper in Earth's gravitational well. The difference is incredibly small, but it is real. Clocks at different altitudes tick at different rates, and this has been measured with extraordinary precision. Near extremely massive objects, the effect becomes dramatic. Close to a black hole where gravity is immense, time slows to a crawl relative to distant observers. Time dilation near black holes is extreme. Black holes are regions of spacetime where gravity is so strong that not even light can escape. Near the event horizon, the boundary beyond which nothing returns, time dilation becomes staggering. If you could somehow survive near a black hole's event horizon and watch the universe beyond, you would see time speeding up dramatically. Stars would live and die in what seems like moments to you. Galaxies would evolve before your eyes. Meanwhile, to someone watching you from a safe distance, you would appear to move in slow motion, your actions stretched out over years or centuries. If you hovered just outside a black hole's event horizon for 1 hour by your watch, thousands or even millions of years might pass in the universe beyond, depending on the black hole's mass. You would have traveled into the future without traveling faster than light. This is real physics. The equations are clear. Time genuinely passes at different rates in different gravitational fields. Particles prove time dilation happens. High in Earth's atmosphere, cosmic rays, high-energy particles from space, collide with atoms in the air. These collisions create particles called muons. Muons are unstable and decay rapidly. On average, a muon lives for only about 2 microseconds before breaking apart into other particles. At the speed muons travel, even moving near the speed of light, they should only travel about 600 meters before decaying. Yet muons created in the upper atmosphere, 15 kilometers high, regularly reach Earth's surface. How is this possible? The answer is time dilation. From our perspective on the ground, the muon's internal clock is running slow because it is moving so fast. What is 2 microseconds to the muon is stretched to a much longer time from our point of view, allowing it to travel farther before decaying. From the muon's perspective, time passes normally for it, but the distance to Earth's surface is contracted because of its high speed. Either way you look at it, relativity makes the journey possible. This is not theoretical. Scientists detect muons at sea level every day. It is direct, observable proof that time dilation is real. The speed of light is the cosmic speed limit. Nothing in the universe can travel faster than light in a vacuum, approximately 300 million meters per second. This is not just a speed limit like those on highways. It is a fundamental property of spacetime itself. As you accelerate toward the speed of light, several strange things happen. Your mass effectively increases, requiring ever more energy to accelerate further. Distances in the direction you are traveling contract, appearing shorter. And time slows down for you relative to the outside universe. At the speed of light itself, time would stop completely, though no object with mass can ever reach this speed. Light itself experiences no time. From a photon's perspective, if it could have one, it is emitted and absorbed in the same instant, even if it travels across the universe for billions of years from our perspective. The speed of light connects space and time in a profound way. The faster you move through space, the slower you move through time, and the relationship is exact and mathematical. This is why the speed of light is the same for all observers, no matter how fast they are moving. It is the one constant in a universe where time and space are flexible. Space-time is a fabric that can bend and stretch. Before Einstein, physicists thought of space as an empty stage where events unfolded, and time as a separate, absolute flow. Einstein unified them into space-time, a single four-dimensional entity. Mass and energy curve this space-time fabric, and objects moving through it follow these curves. This is what we experience as gravity. Imagine a stretched rubber sheet. Place a heavy ball on it, and the sheet curves downward. A smaller ball rolled nearby will curve toward the heavy one, not because of a mysterious force reaching across space, but because it is following the curved surface. This is an imperfect analogy, but it captures the essence. Massive objects curve to space-time, and other objects follow those curves. Light, though massless, also follows these curves, which is why we observe gravitational lensing, where light from distant galaxies bends around massive objects. But space-time does not just curve in space, it curves in time too. Near massive objects, time itself is stretched, flowing more slowly. This curvature affects every aspect of physics, from the orbit of planets to the aging of atoms. Space-time is not just where things happen. It is an active participant in the unfolding of events, a dynamic fabric shaped by matter and energy. You can calculate exactly how much time would change. The mathematics of time dilation are precise and surprisingly accessible. For motion, the time dilation factor depends on velocity. If you travel at 87% the speed of light, time slows down by half for you compared to a stationary observer. For every year you experience, 2 years pass for those at rest. At 99.5% light speed, time slows to a tenth. 1 year for you equals 10 years outside. At 99.995% light speed, 1 year becomes 100 years. The closer you get to light speed, the more dramatic the effect. For gravitational time dilation, the effect depends on how deep you are in a gravitational field. On Earth's surface, compared to far from any mass, time runs slower by about 1 part in a billion. Near the Sun, the effect is stronger. Near a neutron star, dramatically more so. Close to a black hole, time can slow to nearly any degree. These are not vague predictions. They are exact calculations that match every experiment and observation. With the right equipment and trajectory, we could send someone into Earth's future by any amount we choose. The limitation is not the physics, but the engineering, the energy and technology required to reach such speeds or approach such massive objects safely. Simultaneity is not universal. One of the strangest consequences of relativity is the relativity of simultaneity. Events that appear to happen at the same time for one observer may not be simultaneous for another observer moving at a different velocity. Imagine two lightning bolts striking opposite ends of a moving train, and an observer on the platform sees them strike at exactly the same moment. But an observer on the train, moving toward one strike and away from the other, will see one bolt strike before the other because light from the strikes reaches her at different times. This is not an optical trick. In relativity, there is no absolute simultaneity. Different observers can disagree about the order of events, and both are correct. The concept of now, of what is happening at this very moment across the universe, depends on your reference frame. For distant events, different observers moving at different velocities will have different definitions of what now means. This breaks our intuitive notion of time as a universal river flowing at the same rate everywhere. Instead, the universe is more like a vast spacetime landscape, where each observer carves their own path through it. Past, present, and future are not absolute categories, but depend on motion and gravity. This does not mean anything goes or that causality breaks down, but it does mean the universe is far stranger than our everyday experience suggests. Time dilation has been confirmed in particle accelerators. In laboratories around the world, scientists accelerate particles to nearly the speed of light and smash them together. These particles, moving at relativistic speeds, live longer from our perspective than they would if at rest. Unstable particles that normally decay in fractions of a second can survive for much longer when accelerated, because time slows down for them. This is not an interpretation. It is a direct measurement. Physicists must account for time dilation when designing experiments and analyzing data. The Large Hadron Collider, the world's most powerful particle accelerator, routinely deals with time dilation effects. Particles traveling at 99.999% the speed of light experience. Time thousands of times slower than laboratory clocks. This allows unstable particles to travel farther and live longer, enabling scientists to study them in detail. Every collision, every decay, every measurement confirms Einstein's predictions. Time dilation is not a quirky side effect. It is a central feature of high-energy physics, woven into the fabric of how particles behave at extreme speeds. Even your own body is a time machine in miniature. Every atom in your body, every particle, exists within the framework of spacetime. The electrons orbiting atomic nuclei move at significant fractions of the speed of light and experience tiny time dilation effects. The quarks inside protons and neutrons also move at relativistic speeds. These effects are minuscule and have no noticeable impact on your daily life, but they are real. On a fundamental level, different parts of your body, even different particles within a single atom, experience time slightly differently. When you move, time flows differently for you than for someone at rest, though the effect is far too small to measure with current technology. If you spend your life traveling by airplane, you will age slightly less than someone who stays on the ground, by a few dozen nanoseconds perhaps. If you live on a mountain, you age slightly faster than someone at sea level. These effects are real but so tiny they have no practical consequence for human lifespans. Yet they remind us that time is not the simple, universal flow we perceive. It is fluid, flexible, and intimately connected to motion and gravity. We live in a universe where time travel is not just possible but unavoidable. Every moment of your life, you are traveling through time at 1 second per second. But by moving or by entering strong gravitational fields, you can change that rate. You can slow your journey through time relative to others. You can, in a very real sense, travel into the future. The laws of physics allow it. The mathematics describe it. The experiments confirm it. Forward time travel is not science fiction. It is science fact. The only questions remaining are how far we can go, how fast, and whether we will ever develop the technology to make dramatic journeys into the future a reality. As you rest tonight, time flows around you and through you at its steady pace. 1 second per second from your perspective, but infinitely variable depending on how you move through the universe. The clock on your wall, the rhythm of your breath, the gentle passage from waking to sleep, all are manifestations of time's inexorable flow. And somewhere out there, in the vast cosmos, time flows differently. Near black holes, it slows to a crawl. For particles racing through accelerators, it stretches thin. For astronauts in orbit, it ticks just slightly slower. Time is not one thing but many, a dimension as rich and complex as space itself. And in this dimension, travel is possible. You need only move fast enough or fall deep enough into gravity's well. The future awaits, not as a distant dream, but as a destination written into the very laws of nature. Sleep well, knowing that time, mysterious and malleable, carries you gently forward through the night. Near light, speed travel is the most reliable method for traveling into the future. If you want to journey far into Earth's future, the surest way is to travel very fast. Not just fast by everyday standards, but at a significant fraction of the speed of light. At these relativistic speeds, time dilation becomes dramatic. A spacecraft traveling at 90% light speed would experience time passing at less than half the rate of Earth. A journey that feels like 5 years to the travelers would span more than 11 years on Earth. They would return to find the world aged twice as much as they did. At 99% light speed, the effect intensifies. 1 year aboard the ship equals 7 years on Earth. At 99.9%, 1 year becomes 22 years. The mathematics are precise and unforgiving. The closer you approach light speed, the more pronounced the dilation. At 99.999% light speed, a journey lasting 1 year for the crew would mean 447 years pass on Earth. The travelers would step off their ship into a world transformed beyond recognition. Civilizations risen and fallen, technology unrecognizable, everyone they knew long dead. This is not speculation. This is what Einstein's equations predict with absolute certainty. The only barrier is engineering. Building a spacecraft capable of reaching such speeds requires energy on a scale we cannot yet harness, but the physics is sound. If we can solve the engineering challenges, we can send humans into Earth's future by any amount we choose. They would age normally, experience time normally, but the universe around them would race forward. It is the ultimate one-way journey, and it is entirely possible within the known laws of physics. Generation ships would create natural time travelers. Imagine a massive spacecraft designed to travel between stars, carrying thousands of people on a journey spanning decades or centuries. These are called generation ships because multiple generations would live and die aboard before reaching the destination. But if such a ship traveled at relativistic speeds, something remarkable would happen. Time dilation would mean the journey takes less time for those aboard than for people back on Earth. A voyage to a star 20 light-years away, traveling at 90% light speed, would take about 22 years from Earth's perspective. But for the travelers, because of time dilation, only about 9.5 years would pass. They would arrive having aged less than a decade, while more than 2 decades elapsed on Earth. For the crew, the stars would seem closer than the distance light travels, because distances contract at high speeds, another effect of relativity. If the ship traveled even faster, say 99.5% light speed, the crew would experience the journey as lasting less than 2 years, while Earth aged 20 years. The travelers would not feel time passing differently. Their clocks would tick normally. Their hearts would beat at regular rhythms. But when they compared notes with Earth, the discrepancy would be undeniable. They would have traveled into Earth's future. This makes interstellar travel more feasible than it first appears. The galaxy is vast, but time dilation compresses subjective journey times. A trip across the galaxy that would take 100,000 years at light speed would feel much shorter to travelers moving at near light speed. They could cross the Milky Way within a human lifetime from their perspective, emerging into a galaxy aged 100 millennia. Gravitational time dilation offers another path to the future. You do not need to travel fast to experience time differently. You can instead go somewhere with strong gravity. The deeper you descend into a gravitational well, the slower time passes for you relative to someone farther away. Near a neutron star, one of the densest objects in the universe, gravity is so intense that time runs noticeably slower than on Earth. If you could survive on the surface of a neutron star for what feels like 1 hour, several hours might pass for distant observers. The exact ratio depends on the neutron star's mass and radius, but the effect is substantial. Even more extreme is the time dilation near a black hole. Black holes warp spacetime so severely that near the event horizon, time nearly stops relative to the outside universe. If you could hover just outside a supermassive black hole's event horizon, protected somehow from the intense tidal forces and radiation, you could watch the universe age rapidly. Minutes for you could be years, centuries, or millennia outside, depending on how close you are to the horizon. The film Interstellar dramatized this concept with the water planet orbiting the black hole Gargantua. 1 hour on the planet's surface equaled 7 years outside. While the exact numbers depend on the black hole's properties and the planet's orbit, the physics is real. Massive objects slow time, and black holes are the most massive objects per unit volume in existence. Their gravitational time dilation is extreme. You could use this effect to travel into the future without ever exceeding the speed of light. Simply descend close to a black hole's event horizon, remain there for a period, and then escape. When you return to Earth, far more time will have passed than you experienced. You will have traveled forward through time. Time dilation around Sagittarius. A star, our galaxy's supermassive black hole, is significant. At the center of the Milky Way lurks a black hole with a mass of about 4 million suns. This is Sagittarius A star, and it creates a deep gravitational well in spacetime. Stars orbit this black hole at tremendous speeds, some completing an orbit in just over a decade. For these stars, time runs measurably slower than for us out here in the galactic suburbs. If you could travel to the innermost stable orbit around Sagittarius A star, time dilation would be noticeable. At a distance of about 5 times the event horizon radius, a safe orbit where you would not be pulled in, time would pass at roughly 70% the rate of distant regions. 1 year in orbit would equal about 1.4 years elsewhere. Closer still, the effect intensifies. The mathematics shows that as you approach the event horizon, time dilation approaches infinity. Right at the horizon, time from an outside perspective stops completely. But for you falling in, time continues normally. You would cross the horizon in finite time by your watch, but to an outside observer, you would appear frozen at the edge, your image redshifting and fading, but never quite disappearing. This strange asymmetry is a consequence of how black holes warp spacetime. Different observers experience drastically different realities. There is no paradox here, just the profound strangeness of a universe where time is flexible. Rotating black holes offer even stranger possibilities. Not all black holes are simple spheres of collapsed matter. Many rotate, spinning at tremendous speeds. These are called Kerr black holes, after physicist Roy Kerr, who first described their properties mathematically. Rotating black holes have an event horizon like non-rotating ones, but they also have another boundary called the ergosphere, a region outside the event horizon, where spacetime itself is dragged around by the black hole's rotation. Inside the ergosphere, nothing can remain stationary. Everything, even light, is pulled along in the direction of the black hole's spin. But you can still escape from the ergosphere, unlike from inside the event horizon. Theoretically, the rotation of a Kerr black hole creates even stranger effects. Some solutions to Einstein's equations suggest that inside a rotating black hole, paths through spacetime could loop back on themselves, forming closed time-like curves. These are paths through spacetime that return to their own past. If they exist, and that is a significant if, you could in theory follow such a curve and arrive back at an earlier moment in your own timeline. This ventures into highly speculative territory. The interior of a black hole is hidden behind the event horizon, and we cannot observe what happens there directly. The mathematics allows for these closed time-like curves, but many physicists suspect that other effects, perhaps quantum ones we do not yet understand, would prevent them from forming. The interior of a Kerr black hole might contain a ring singularity rather than a point, and passing through this ring could theoretically lead to another region of spacetime. But whether this is physically real or merely a mathematical curiosity remains unknown. What is certain is that rotating black holes are real, and their ergospheres have been indirectly detected. The rest is tantalizing possibility. Tipler cylinders are theoretical time machines based on rotation. In 1974, physicist Frank Tipler proposed a thought experiment involving an infinitely long, extremely dense cylinder rotating at relativistic speeds. Such an object would drag spacetime around with it so severely that closed time-like curves would form in the surrounding space. If you traveled around the cylinder in a specific path at a specific speed, you could theoretically arrive back at your starting point in space before you left in time. You would have traveled into your own past. The Tipler cylinder is a solution to Einstein's equations, meaning the math works. General relativity permits its existence. However, building one is another matter entirely. It would require infinite length and enormous density, likely involving exotic matter with properties we have never observed. Some versions of the concept use finite cylinders, but these require even stranger conditions, such as matter with negative energy density, to generate closed time-like curves. No one has ever detected negative energy density matter in bulk, though quantum effects like the Casimir effect hint that it might exist on tiny scales. The Tipler cylinder remains a theoretical curiosity, a proof that Einstein's equations allow for time travel to the past under certain extreme conditions. Whether the universe actually permits such structures to exist is another question. Many physicists suspect that unknown laws, perhaps related to quantum gravity, would prevent Tipler cylinders from forming or would destroy them if created. Still, the fact that the mathematics of general relativity allows for past-directed time travel at all is remarkable. The universe may be stranger than we imagine. Cosmic strings could bend spacetime enough for time travel. In the early moments after the Big Bang, as the universe cooled and underwent phase transitions, defects might have formed in the fabric of spacetime itself. One hypothetical type of defect is a cosmic string, an incredibly dense, thin filament of energy stretching across vast distances. If cosmic strings exist, they would have enormous mass concentrated along a one-dimensional line, creating intense gravitational fields around them. Two cosmic strings moving past each other at high speeds could, in theory, warp spacetime enough to create closed time-like curves in the region between them. An object following the right trajectory around these strings could arrive back at its own past. The geometry is complex, but the mathematics checks out within general relativity. Cosmic strings have never been directly detected. If they exist, they are likely rare and difficult to observe. Astronomers have searched for their gravitational effects, such as duplicate images of galaxies lensed by a string's gravity, but no definitive evidence has emerged. Even if cosmic strings exist, using them for time travel would be extraordinarily difficult. You would need two of them, moving at precisely the right speeds, and you would need to navigate a path around them with incredible precision. Any mistake would likely result in being torn apart by tidal forces or flung off course. Still, cosmic strings represent another way that the laws of physics might permit time travel, at least in principle. They are a reminder that general relativity, while well tested in many regimes, still holds surprises, and the universe may contain structures and phenomena we have not yet imagined. The Alcubierre warp drive might allow faster-than-light travel. In 1994, physicist Miguel Alcubierre proposed a theoretical method for traveling faster than light without violating relativity. The idea is to contract spacetime in front of a spacecraft and expand it behind, creating a bubble of normal spacetime that surfs along on a wave of compressed and stretched space. From the perspective of distant observers, the bubble could move faster than light, but the spacecraft inside remains stationary relative to the space immediately around it. No local speed limit is broken because the spacecraft is not moving through space. Space itself is moving. The Alcubierre drive is mathematically consistent with general relativity, but it requires exotic matter with negative energy density to function. This is the same problematic requirement that plagues many time travel concepts. Negative energy density matter would create a repulsive gravitational effect, pushing spacetime rather than pulling it. Small amounts of negative energy have been detected in quantum experiments, such as the Casimir effect, but scaling this up to the quantities needed for a warp drive is far beyond current technology and may be impossible. If an Alcubierre drive could be built, and if it could travel faster than light, It might also enable time travel. Faster than light travel in one reference frame looks like backwards time travel in another, due to the relativity of simultaneity. You could potentially create a closed time-like curve by making two warp drive journeys in different directions, arriving back in time before you left. This has led some physicists to argue that if warp drives are possible, time travel to the past might be too. Others suggest that unknown effects would prevent this, preserving causality. The Alcubierre drive remains speculative, a tantalizing idea that shows how the laws of physics might permit what seems impossible, but only under conditions we cannot currently create. Energy requirements for future time travel are mostly achievable with advanced technology. Traveling into the future via time dilation does not require breaking any laws of physics. It simply requires energy, lots of it, to accelerate a spacecraft to relativistic speeds, or to navigate close to a massive object. Consider accelerating a spacecraft to 90% light speed. The energy required grows dramatically as you approach light speed, because relativistic mass increases. For a spacecraft with a rest mass of 1,000 tons, accelerating it to 90% light speed would require kinetic energy equivalent to about 2.5 times 10 to the 20 joules. That is roughly the total energy output of the Sun over 1 second, or about 500 million times the annual energy consumption of all humanity. This is an enormous amount, but not infinite. With advanced enough technology, such as fusion drives, antimatter engines, or direct energy beam propulsion, it could be achievable in principle. The laws of physics do not forbid it. The engineering challenges are immense, but they are not insurmountable given enough time and resources. For gravitational time travel, no energy is required to simply fall toward a massive object. You could coast into orbit around a black hole using gravity alone. The challenge is escaping afterward, which requires energy proportional to how deep into the gravitational well you descended. The deeper you go, the stronger the time dilation effect, but the more energy you need to climb back out. Still, compared to the exotic requirements of wormholes or warp drives, using gravity for time travel is relatively straightforward. Black holes exist. We know where they are. With sufficiently advanced spacecraft, we could reach them. The universe provides natural time machines in the form of massive objects. We need only the means to reach them and the will to make the journey. Cryogenic suspension is not time travel, but it mimics the effect. Science fiction often depicts travelers frozen in cryosleep, waking decades or centuries later to find themselves in the future. This is not time travel in the relativistic sense. If you are frozen and then thawed, you have not altered the flow of time. You have simply been unconscious. The universe aged around you at its normal rate. You aged too, though biological processes were halted or drastically slowed. From a physics perspective, cryogenic suspension does not involve time dilation or any alteration of spacetime. It is biological stasis, not temporal displacement. That said, the subjective experience would be similar. You close your eyes in one era and open them in another, having experienced no time passing. To you, the future has arrived instantly. But there is a crucial difference. With relativistic time travel, time genuinely passes more slowly for you. You could carry an atomic clock with you, and it would tick slower than clocks on Earth, confirming that time itself was dilated. With cryogenic suspension, your clock and Earth's clock remain synchronized. You simply were not conscious to observe the ticking. cryogenic technology does not exist yet in any reliable form. Freezing a human body causes ice crystals to form, damaging cells. Some animals can survive freezing, but mammals cannot without extensive damage. Research into cryopreservation continues, with the hope that future technology might allow revival. If successful, it would enable long-duration space travel without time dilation, allowing crews to sleep through voyages lasting centuries. But it would not be time travel. It would be a very long nap in a very cold bed. Gravitational time dilation near neutron stars is extreme. Neutron stars are the collapsed cores of massive stars, crushed by supernova explosions into spheres only about 20 kilometers across, but containing more mass than the Sun. Their density is staggering, comparable to an atomic nucleus. A sugar cube of neutron star matter would weigh about 1 billion tons on Earth. Gravity at a neutron star's surface is roughly 100 billion times stronger than Earth's. This creates severe time dilation. At the surface of a typical neutron star, time runs at about 70 to 80%, the rate of distant space, depending on the star's exact mass and radius. If you could stand on a neutron star's surface for 1 hour, about 15 minutes more would pass for someone far from any gravitational influence. The effect is noticeable, but not as extreme as near a black hole. However, getting close to a neutron star is extraordinarily dangerous. The tidal forces would stretch and compress anything approaching, a process gruesomely termed spaghettification. The intense magnetic fields, often trillions of times stronger than Earth's, would disrupt atomic structures. The surface temperature can exceed 1 million degrees, and the radiation environment is lethal. Neutron stars emit powerful beams of X-rays and gamma rays. Some, called pulsars, sweep these beams across space as they rotate, creating a lighthouse effect. Approaching one would expose you to radiation doses fatal within seconds. Still, if you could somehow survive or observe from a safe distance, neutron stars offer a glimpse of extreme gravitational time dilation in action, a stepping stone between normal spacetime and the even stranger realm of black holes. The journey around a Kerr black hole might lead somewhere unexpected. In the mathematics of rotating black holes, the singularity is not a point but a ring. This ring singularity spins at the center, and the equations suggest that passing through it might not crush you into oblivion. Instead, it could lead to another region of spacetime, perhaps another universe, or another part of our own universe. This is highly speculative. The interior of a black hole is causally disconnected from the outside universe. Anything that crosses the event horizon cannot send information back. We rely on mathematical solutions to Einstein's equations to speculate about what lies inside. And these solutions, while mathematically valid, may not reflect physical reality. They might be artifacts of the equations, interesting possibilities that nature does not actually realize. Even if the ring singularity does lead somewhere, getting there would be nearly impossible. You would have to enter the black hole, survive the intense tidal forces near the event horizon, navigate through the interior without hitting the singularity, and somehow pass through the ring at just the right angle. The slightest deviation would be catastrophic, and once inside, there is no coming back. The event horizon is a one-way membrane. You can cross inward, but never outward. Even if you emerged into another region of space-time, you would be trapped there, unable to return and report your findings. Still, the idea captures the imagination. Black holes are not just endpoints, not just cosmic trash compactors, but potentially gateways, doors in space-time leading to unknown destinations. Whether these doors open onto anything real or simply into mathematical fantasy, we do not yet know. Time dilation has been measured on airplanes carrying atomic clocks. In 1971, physicists Joseph Haffel and Richard Keating performed a famous experiment. They flew atomic clocks around the world on commercial airplanes, once eastward and once westward, and compared them to clocks that remained on the ground. General relativity predicted that the flying clocks would experience less gravity and would therefore tick slightly faster than ground clocks. Special relativity predicted that the flying clocks, moving relative to the ground, would tick slightly slower. The two effects compete, and the net result depends on the flight direction and speed. The westward flight, moving against Earth's rotation, experienced a net time gain. The eastward flight experienced a net time loss. When the clocks were compared, the differences matched Einstein's predictions to within experimental error. The westward clock gained about 273 nanoseconds. The eastward clock lost about 59 nanoseconds. These are tiny fractions of a second, but they are measurable and they confirm that time dilation is real. Similar experiments have been repeated with greater precision using better clocks and GPS satellites. Every result confirms relativity. Time genuinely passes at different rates depending on motion and gravity. You can take a clock on a fast airplane and prove it yourself, though you would need an atomic clock to measure the tiny difference. The fact that such experiments work, that clocks flown around the world show predicted time differences, is direct empirical evidence that time travel into the future happens. The effects are small in everyday circumstances, but they scale up. Go fast enough or fall deep enough, and the effects become dramatic. Near light speed journeys would feel normal to travelers. If you boarded a spacecraft and accelerated to 99% light speed, you would not feel time slowing down. Your heartbeat would remain steady. Your thoughts would unfold at their usual pace. Clocks aboard the ship would tick normally. From your perspective, nothing unusual would happen. Time dilation is not something you experience directly. It is a relationship between your time and time in other reference frames. Only when you compare your clock to a clock in a different reference frame do you notice the difference. If you looked out the window of your relativistic spacecraft, you would see strange effects. Stars ahead would appear blue, shifted, their light compressed to higher frequencies. Stars behind would redshift, stretching toward lower frequencies. The star field would appear distorted, bunched up ahead of you due to relativistic beaming. If you could somehow observe Earth, you would see time moving faster there. People would age rapidly from your perspective, days and years flashing by in moments. But aboard your ship, everything would be normal. You would eat, sleep, read, think, just as you always have. The strangeness of relativity is not in how you experience your own time, but in how your time relates to others. When you returned to Earth after a journey at 99% light speed, you might have aged 1 year while Earth aged 7. To you, only 1 year passed. To Earth, 7 years passed. Both are true. Both are valid measurements of time. There is no contradiction, only the profound flexibility of time in a relativistic universe. The galaxy is full of natural time dilation laboratories. Every black hole, every neutron star, every massive object is a place where time runs differently. The universe is not a uniform stage where time ticks at one universal rate. It is a landscape of temporal variation, with fast-flowing time in empty space and slow time near massive objects. Astronauts orbiting Earth experience slightly less time. Satellites experience even less. Light skimming the sun's surface experiences gravitational time dilation. Particles accelerated in colliders experience kinetic time dilation. All around us, in ways large and small, time flows at different rates. We do not notice most of these effects because they are tiny in our everyday environment, but they are real and measurable. The universe is a vast laboratory for studying time, and every precise measurement we make confirms Einstein's insights. From GPS satellites to pulsar timing to gravitational wave detections, the evidence is overwhelming. Time is not absolute. It bends, stretches, and flows at rates determined by motion and gravity. This is not a strange quirk of exotic conditions. It is a fundamental property of the universe we inhabit. Every journey you take, every step you climb, every moment you exist, you are experiencing time dilation, even if the effect is too small to notice. You are already a time traveler, moving through the fourth dimension at a rate determined by your motion and position in spacetime. The only question is how far into the future you wish to go, and whether you have the means to make the journey. The grandfather paradox is the most famous problem with backward time travel. Imagine you build a time machine and travel back to a time before your parents were born. You find your grandfather as a young man, and, for whatever reason, you prevent him from meeting your grandmother. They never marry, your parent is never born, and therefore you are never born. But if you were never born, you could not have traveled back in time to prevent your grandparents from meeting. So they do meet. Your parent is born, you are born, and you do travel back in time to prevent their meeting. The loop is paradoxical, a logical contradiction with no resolution. This is the essence of the grandfather paradox, and it reveals why traveling to the past is so much more problematic than traveling to the future. The future is open, undetermined, and traveling there creates no logical problems. You simply skip forward, experiencing less time than the rest of the universe. But the past has already happened. Events have unfolded in a specific way, leading to the present moment. If you could change the past, you could create contradictions, situations where causes and effects become tangled in impossible ways. The grandfather paradox is not just a thought experiment. It is a serious challenge to the possibility of backward time travel. If traveling to the past is possible, the universe must have some mechanism to prevent paradoxes, or perhaps paradoxes indicate that backward time travel is simply impossible. The bootstrap paradox involves information with no origin. Imagine you receive a book from your future self containing the complete works of Shakespeare. You read the book, memorize it, and then when you are older, you travel back in time and give the book to your younger self. Where did the information in the book come from? Shakespeare did not write it in this timeline. You did not create it. The book exists in a closed loop, given to you by your future self, who received it from their future self, and so on infinitely backward. The information has no origin point, no moment of creation. This is the bootstrap paradox, also called an ontological paradox. It applies not just to information but to objects and even people. Suppose you travel back in time and become your own grandfather by having a child with your grandmother. You are part of your own family tree, a loop with no beginning. These scenarios are logically coherent in a narrow sense. There is no contradiction within the loop itself. but they violate our intuition about causality. Effects should have causes, and those causes should precede the effects in time. In a bootstrap paradox, causality becomes circular. The book causes itself to exist. You cause yourself to exist. Many physicists find this deeply troubling, a sign that backward time travel might not be possible. Others suggest that if time travel is possible, bootstrap paradoxes might be unavoidable, and we must accept that causality in a time travel universe is stranger than we thought. Causality violation means effects preceding causes, breaking physics. The laws of physics as we understand them assume causality. Causes precede effects. A ball breaks a window because someone threw it, not the other way around. Heat flows from hot to cold. Entropy increases, and time has an arrow pointing from past to future. If you could travel to the past and change events, you could create situations where effects precede their causes. You could receive a message before it was sent. You could be injured by a weapon that was destroyed before it fired. These violations of causality are not just philosophical problems. They threaten the entire structure of physics. Our equations describe how causes lead to effects, how initial conditions determine future states. If effects can precede causes, these equations lose their predictive power. Physics becomes indeterminate, perhaps even incoherent. Some solutions to Einstein's equations, such as those involving rotating black holes or wormholes, contain closed time-like curves, paths through spacetime that loop back to an earlier time. These solutions allow for backward time travel in principle. But do they represent physical reality, or are they mathematical curiosities that nature does not permit? Many physicists suspect the latter. Stephen Hawking proposed the chronology protection conjecture, the idea that unknown laws of physics prevent the formation of closed time-like curves, preserving causality. We do not yet have a complete theory of quantum gravity, which would unite general relativity and quantum mechanics. Such a theory might reveal why backward time travel is impossible, even if the equations of relativity seem to allow it. The Novikov self-consistency principle suggests the universe prevents paradoxes. In the 1980s, physicist Igor Novikov proposed a solution to the paradoxes of time travel. His self-consistency principle states that if time travel to the past is possible, events must arrange themselves so that paradoxes cannot occur. You might travel back in time intending to kill your grandfather, but something always prevents you from succeeding. Your gun jams, you slip and miss. You change your mind. Or you discover the man you thought was your grandfather is actually someone else. The universe conspires to maintain consistency. In this view, the past is fixed and immutable. You can travel to the past, and you can be present in past events, but you cannot change what happened. Whatever you do in the past was always part of the past. There is only one timeline, one history, and it includes your time travel. This eliminates paradoxes because there is no alternative history where you did not travel back. If you gave your younger self a book, then you always received that book from your older self. The loop is closed and consistent. The self-consistency principle is elegant, but it raises troubling questions about free will. If the past cannot be changed, do you have any choice in what you do when you travel there? Or are your actions predetermined, forced by the need to maintain consistency? Some physicists find this acceptable, arguing that free will is an illusion anyway. Others find it unsatisfying, preferring interpretations where backward time travel is simply impossible. Closed, time-like curves are paths through space-time that loop back. In general relativity, a time-like curve is a path through spacetime that an object with mass could follow, always moving slower than light. Normally, such paths extend from past to future, never looping back. But in certain solutions to Einstein's equations, closed time-like curves can exist. These are paths that circle through spacetime and return to their own past. If you followed a closed time-like curve, you would travel forward through time from your perspective, always moving into your future, but the geometry of spacetime would be such that your future eventually intersects your past. You would arrive at a moment before you left without ever traveling backward through time from your viewpoint. Closed time-like curves appear in the mathematics of rotating black holes, infinitely long rotating cylinders, certain wormhole configurations, and other exotic spacetime geometries. Their presence in the equations does not necessarily mean they exist in reality. Many physicists believe that quantum effects, not accounted for in classical general relativity, would prevent closed time-like curves from forming. The enormous energy densities or exotic matter required might be unattainable. Or perhaps the formation of a closed time-like curve triggers a catastrophic instability that destroys it. The universe might have a built-in mechanism, as yet unknown, that forbids these structures. Alternatively, closed time-like curves might be possible, and the universe might accommodate them through self-consistency. Experiments with particles and quantum systems have explored closed time-like curve-like behavior on tiny scales, and the results are intriguing but not conclusive. The question remains open, tantalizing, and unresolved. Quantum mechanics and many worlds might resolve paradoxes. One interpretation of quantum mechanics, the many worlds interpretation, suggests that every quantum measurement causes the universe to split into multiple branches, each representing a different outcome. In this view, there is not one universe but an ever-branching tree of universes, encompassing all possible histories. If backward time travel is possible in a many worlds framework, paradoxes might be avoided by branching. Suppose you travel back in time and kill your grandfather. In the original timeline, he lived and you were born. But by killing him, you create a new branch where he dies, and you are never born in that branch. You still exist because you came from a different branch, but the timeline you are now in does not lead to your birth. There is no paradox because the two timelines are separate. This resolves the grandfather paradox, but at a cost. You cannot change your own past. You can only create alternate pasts in other branches. The timeline you came from remains unchanged, existing in a separate branch of the multiverse. If you travel back and give yourself a winning lottery ticket, the version of you that receives the ticket is in a different branch. Your original self does not benefit. Some physicists find this interpretation appealing because it preserves logical consistency while allowing time travel. Others find it extravagant, multiplying universes without limit. The many worlds interpretation remains controversial, with passionate advocates and detractors. If it is correct, and if time travel is possible, then the universe is far stranger and more vast than we imagine. An infinite forest of branching timelines where every possibility is realized somewhere. Wormholes are shortcuts through spacetime. In general relativity, a wormhole is a tunnel connecting two distant points in spacetime. Imagine spacetime as a two-dimensional sheet. A wormhole is like folding the sheet so 2 points touch and then creating a tunnel between them. Instead of traveling the long way across the sheet, you take the shortcut through the tunnel. Wormholes are solutions to Einstein's equations, discovered in the early 20th century by physicists studying black holes. Initially, they were thought to be non-traversable, collapsing too quickly for anything to pass through. But in the 1980s, physicist Kip Thorne and his colleagues showed that a wormhole could theoretically be held open if it contained exotic matter with negative energy density. Such matter would create a repulsive gravitational effect, pushing spacetime apart rather than pulling it together. This would prevent the wormhole from collapsing. If traversable wormholes exist, they could connect distant parts of the universe, allowing travel across vast distances in short times. You could enter a wormhole on Earth and emerge near a distant star, having traveled thousands of light years through the tunnel in moments. But wormholes could also connect different times. If one mouth of a wormhole is accelerated to near light speed, or placed near a massive object, time dilation would cause time to pass differently at that mouth compared to the other. Eventually, the two mouths would be separated in time as well as space. Entering one mouth could bring you out the other at an earlier time. The wormhole becomes a time machine. Wormholes collapse without exotic matter to stabilize them. The problem with wormholes is that they are unstable. According to the equations, a wormhole without exotic matter will collapse almost instantly, pinching off before anything can travel through. To keep a wormhole open, you need matter with negative energy density, something that creates outward pressure rather than inward gravitational attraction. Does such matter exist? On macroscopic scales, we have never observed it. All normal matter has positive energy density and creates attractive gravity. However, quantum mechanics predicts that negative energy density can exist on tiny scales. The Casimir effect, observed in laboratories, involves two uncharged metal plates placed very close together in a vacuum. Quantum fluctuations in the vacuum create a pressure difference between the plates and the surrounding space, pushing the plates together. This can be interpreted as the region between the plates having a slightly negative energy density. The effect is real and measurable, confirming that negative energy exists in some form. But the amount is tiny, far too small to stabilize a human traversable wormhole. Scaling up the Casimir effect to macroscopic levels would require conditions we do not know how to create. Some physicists speculate that advanced civilizations might find ways to manipulate quantum fields to generate large amounts of negative energy. Others doubt it is possible, suggesting that unknown principles of physics limit how much negative energy can be concentrated. Without exotic matter, wormholes remain theoretical curiosities, solutions to equations that may not correspond to anything in the real universe. With exotic matter, they become potential time machines, and the door to the past swings open. Negative energy and the Casimir effect prove strange things are possible. The Casimir effect is one of the most fascinating predictions of quantum mechanics. In a vacuum, we usually think of empty space as truly empty, containing nothing. But quantum field theory tells us that even empty space seethes with activity. Virtual particles constantly pop into existence and annihilate, borrowing energy from the vacuum for brief moments. These fluctuations are real and have measurable effects. When two uncharged metal plates are placed very close together, certain wavelengths of virtual particles cannot fit between the plates, but all wavelengths can exist outside. This creates an imbalance in the quantum vacuum pressure, pushing the plates together. The effect is weak, requiring sensitive equipment to measure, but it has been confirmed in many experiments. The Casimir effect implies that the vacuum between the plates has lower energy than the vacuum outside, effectively negative energy relative to normal empty space. This is not the same as negative mass or exotic matter in the sense needed for wormholes, but it proves that quantum mechanics allows for conditions that classical physics would consider impossible. If the Casimir effect can be harnessed or scaled up, it might provide the exotic matter needed to stabilize a wormhole. This remains highly speculative, but it is not pure fantasy. The universe already demonstrates that negative energy can exist. The challenge is creating it in sufficient quantities and controlling it in the precise ways needed for time travel or wormhole construction. The chronology protection conjecture says physics prevents time machines. Stephen Hawking was deeply troubled by the possibility of time travel to the past. While he acknowledged that the equations of general relativity permit closed time-like curves under certain conditions, he suspected that nature would find a way to prevent them. In 1992, he proposed the chronology protection conjecture, a hypothesis that the laws of physics conspire to prevent the formation of time machines. Hawking suggested that whenever conditions arise that might create a closed time-like curve, quantum effects would intervene. For example, as you try to create a time machine, perhaps by manipulating a wormhole, quantum fluctuations in the vacuum might build up to infinite levels, creating a catastrophic burst of energy that destroys the time machine before it can function. This is not just speculation. Calculations show that as a wormhole is adjusted to become a time machine, the stress energy of quantum fields near the wormhole grows dramatically. Some solutions suggest this energy diverges to infinity at the moment the time machine would activate. If true, this would make time machines impossible, not because of any simple barrier, but because the universe itself sabotages them. The chronology protection conjecture is not a proven law. It is a hypothesis, a guess about how a complete theory of quantum gravity might behave. We do not yet have such a theory, so we cannot confirm or refute Hawking's idea. It remains an open question, one of the deepest in theoretical physics. Does the universe allow time travel to the past, or is there some fundamental principle we have yet to discover that forbids it? Until we have a theory that unifies quantum mechanics and general relativity, we cannot answer with certainty. Wormholes might exist naturally or require construction. If wormholes are possible, did they form naturally in the early universe, or must they be constructed by advanced civilizations? Some physicists speculate that in the chaotic conditions of the Big Bang, when space-time was wildly fluctuating, tiny wormholes might have formed. These primordial wormholes could persist to the present day, though they would be microscopic and possibly unusable for travel. Alternatively, wormholes might require deliberate construction, the product of a technology far beyond our current capabilities. To create a wormhole, you would need to manipulate space-time on extreme scales, perhaps by concentrating enormous amounts of energy or exotic matter in precise configurations. Some theoretical proposals involve colliding black holes or creating intense gravitational fields using advanced machinery. Even if wormholes exist naturally, making them traversable would require modifications. You would need to thread them with exotic matter to prevent collapse and enlarge them to sizes suitable for spacecraft or people. This assumes that exotic matter can be produced and controlled, which is far from certain. No one has ever observed a wormhole, natural or artificial. We have no evidence they exist outside of mathematical solutions to Einstein's equations. Searches for wormholes in astronomical data have come up empty. If they exist, They are either extremely rare, extremely small, or hidden in ways we have not yet learned to detect. The universe may be filled with wormholes, a network of shortcuts threading through spacetime, or they may be impossible, mathematical phantoms that reality does not permit. Converting a wormhole into a time machine requires time dilation. Suppose you have a traversable wormhole, stabilized with exotic matter, connecting two locations in space. Both mouths of the wormhole are in the present moment, synchronized in time. If you enter one mouth, you emerge from the other at the same time. This is a space shortcut, not a time machine. To turn it into a time machine, you need to create a time difference between the two mouths. One way to do this is through time dilation. Take one mouth of the wormhole and accelerate it to near light speed while leaving the other mouth stationary. As the moving mouth travels, time passes more slowly for it due to kinetic time dilation. After a period, bring the moving mouth to rest near the stationary mouth. The two mouths are now separated in time as well as space. The stationary mouth has aged more than the moving mouth. If you enter the stationary mouth, you emerge from the moving mouth at an earlier time. You have traveled into the past by an amount equal to the time difference created by the journey. This method, proposed by physicists including Kip Thorne, is theoretically sound within general relativity, assuming traversable wormholes are possible. The amount of past you can reach depends on how long the moving mouth traveled and how fast. You cannot travel back to a time before the wormhole was created. The time machine only allows travel within the window between when the two mouths were synchronized and the present. This limits the usefulness of wormhole time machines, but avoids some paradoxes. You cannot travel back to kill your grandfather, because he lived before the wormhole existed. Energy requirements for wormhole time machines are astronomical. Creating and stabilizing a wormhole, then manipulating it into a time machine, would require energy and exotic matter on scales almost beyond comprehension. Estimates vary depending on the wormhole's size and properties, but even a modest human traversable wormhole might require negative energy equivalent to the mass energy of a planet or star. For perspective, converting the mass of Jupiter entirely into energy, following Einstein's famous equation E equals mc squared, yields about 10 to the 43 joules. This is an incomprehensibly large amount. Humanity's total annual energy consumption is around 10 to the 20 joules, more than 20 orders of magnitude smaller. Creating a wormhole might require energy millions or billions of times greater still. Accelerating one mouth of the wormhole to near light speed adds another layer of difficulty. Moving a massive object, even one as exotic as a wormhole mouth, to relativistic speeds requires enormous energy. And you must do this without destroying the wormhole's structure or the exotic matter holding it open. Some physicists have explored whether microscopic wormholes could serve as time machines for information, if not for objects. Sending signals through a tiny wormhole would require far less energy, though still more than we can currently muster. Others doubt that even advanced civilizations could gather the necessary resources. The energy requirements might exceed what is available in an entire galaxy. If wormhole time machines are possible, they may be the province of only the most advanced and ancient civilizations, or they may remain forever theoretical, forever out of reach. Why you would be destroyed inside a black hole. Black holes present their own challenges for time travel. While the intense gravity near a black hole can create dramatic time dilation, Actually, using a black hole as a time machine is fraught with danger. As you approach a black hole, tidal forces increase. Gravity pulls harder on the side of your body, closer to the black hole than the side farther away. This difference, the tidal force, stretches you along the direction toward the black hole and compresses you perpendicular to it. Near a stellar mass black hole, the tidal forces at the event horizon are lethal, strong enough to tear apart any structure, even atoms. Your body would be stretched into a thin stream of particles, a process called spaghettification. Larger black holes have weaker tidal forces at their event horizons because the horizon is farther from the singularity. Near a supermassive black hole like Sagittarius A star, you could cross the event horizon without being immediately torn apart. But once inside, your fate is sealed. You cannot escape. All paths lead to the singularity at the center, where space-time curvature becomes infinite, and physics as we know it breaks down. What happens at the singularity is unknown. General relativity predicts infinite density and infinite tidal forces, but these infinities suggest the theory has reached its limits. A complete theory of quantum gravity would be needed to describe the singularity, and we do not have such a theory. Most physicists suspect you would be destroyed utterly, your information possibly lost forever, though debates about black hole information paradoxes continue. Using a black hole for time travel requires staying outside the event horizon, where time dilation is strong, but escape is still possible. This is dangerous, but theoretically achievable. Gödel's rotating universe allows time loops. In 1949, mathematician Kurt Gödel, famous for his incompleteness theorems, discovered an unusual solution to Einstein's equations. Gödel's universe is a cosmological model where the entire universe rotates. In such a universe, space-time is twisted in a way that allows for closed time-like curves. You could travel far enough in one direction and return to your starting point in space and time, arriving before you left. Gödel presented this solution to Einstein as a birthday gift, and Einstein was reportedly disturbed by it. The idea that his equations allowed for time travel to the past was troubling. However, Gödel's universe does not match our own. Observations show that our universe is expanding and not rotating in the way Gödel's model requires. The cosmic microwave background radiation, the afterglow of the Big Bang, is remarkably uniform in all directions, which would not be the case in a rotating universe. So, while Gödel's universe is a valid mathematical solution, it does not describe reality. Still, Gödel's work showed that general relativity is rich with possibilities, including time travel. The equations do not automatically forbid closed time-like curves. Whether nature permits them is a separate question, one that depends on the actual properties of our universe and on laws of physics we may not yet fully understand. Gödel's universe remains a fascinating curiosity, a reminder that space-time can be far stranger than our intuition suggests. Van Stockham's rotating cylinders also create closed time-like curves. In the 1937, physicist Willem van Stockham studied the space-time around infinitely long rotating cylinders of matter. He found that if such a cylinder rotates fast enough and has sufficient density, it drags space-time around with it, creating closed time-like curves in the surrounding region. This is similar to the Tipler cylinder concept, but predates it. An object traveling around the cylinder in the right way could return to its own past. Like many time travel solutions, Van Stockham's cylinders require extreme conditions. The cylinder must be infinitely long, or at least extremely long, and it must rotate at a significant fraction of the speed of light. The material composing the cylinder must withstand enormous stresses without flying apart. These requirements make Van Stockum cylinders impractical, to say the least. No known material could survive the conditions, and creating an infinitely long structure is obviously impossible. Still, the Van Stockum solution is another proof that general relativity permits time travel under certain geometries. It is part of a broader pattern. Whenever you have rotation, mass, and extreme conditions, space-time can twist into configurations that allow time loops. Whether any of these configurations can be realized in the physical universe is doubtful. They may be mathematical curiosities, interesting features of the equations that do not correspond to anything real. Or they may hint at possibilities we have not yet imagined, ways to manipulate space-time that future civilizations will discover. The Alcubierre drive revisited for time travel possibilities. Earlier, we discussed the Alcubierre drive as a method for faster-than-light travel. But if you can travel faster than light, can you also travel in time? The answer, strangely, is yes, at least according to relativity. Faster-than-light travel in one reference frame appears as backward time travel in another reference frame due to the relativity of simultaneity. If you could make two journeys using an Alcubierre drive, traveling in different directions at faster-than-light speeds, you could theoretically create a closed time-like curve and arrive back before you left. The geometry is complex, but the conclusion is clear. Faster-than-light travel and time travel are closely linked in relativity. If one is possible, the other may be too. This has led some physicists to propose that any method of faster-than-light travel, including warp drives and wormholes, could be converted into a time machine. It also strengthens arguments for the chronology protection conjecture. If faster-than-light travel inevitably leads to time travel, and if time travel creates paradoxes, then perhaps the universe forbids faster-than-light travel as well, not by fiat, but through physical mechanisms we have yet to discover. The Alcubierre drive remains entirely theoretical. No one has created exotic matter in the quantities needed, and it is unclear whether the drive would actually function as the equations suggest. But it serves as a useful thought experiment, revealing deep connections between space, time, and causality. In a universe governed by relativity, these concepts are not separate but intertwined. Manipulating one affects the others in ways both fascinating and troubling. Quantum time travel sending particles backward has been achieved. On the scale of quantum mechanics, time behaves even more strangely than in relativity. Certain quantum experiments have demonstrated effects that seem to involve particles influencing their own past. In 2014, Australian physicists performed an experiment inspired by John Wheeler's delayed choice thought experiment. They sent photons through a setup where the configuration of the experiment was chosen after the photons had already entered. According to classical thinking, the photons should have already decided whether to behave as particles or waves. But the results showed that the photons' behavior depended on the choice made after they entered, as if information traveled backward in time. This does not mean a signal was sent to the past in a way that could create paradoxes. Quantum mechanics is subtle, and interpretations vary. Some physicists argue that the delayed choice experiment shows that quantum systems do not have definite properties until measured. Others suggest it reveals something deep about the nature of time at quantum scales. In another set of experiments, researchers have successfully sent quantum information backward through simulated closed time-like curves. Using quantum entanglement and clever experimental setups, they created conditions where a quantum system's state depends on its own future measurement. These experiments are not time travel in the sense of sending macroscopic objects to the past, but they push the boundaries of what is possible. They suggest that at the quantum level, time may not flow in a simple linear fashion. Cause and effect become blurred. The future can influence the past in ways that do not create paradoxes, but do challenge our understanding. Quantum mechanics and time travel remain an active area of research, full of surprises and unresolved questions. The delayed choice quantum eraser shows particles knowing the past changes. In the world of quantum mechanics, some of the strangest experiments involve what seems to be information traveling backward through time. The delayed choice quantum eraser experiment, first proposed by physicists in the 1980s and performed in various forms since, demonstrates something profound about the nature of reality. In this experiment, photons are sent through a double-slit apparatus. Normally, this creates an interference pattern, waves overlapping and creating bands of light and dark. But if you place detectors to determine which slit each photon passes through, the interference pattern disappears. The act of measurement changes the outcome. The quantum eraser adds a twist. After the photons pass through the slits, their paths are marked in a way that could reveal which slit they used. But then, using clever optical tricks involving beam splitters and detectors, this which path information is erased for some photons but not others. The choice to erase or not erase is made after the photons have already passed through the slits, and even after they have hit the detection screen. According to classical thinking, the photons should have already decided whether to create an interference pattern or not. But the results show that when the which path information is erased, even after detection, the subset of photons involved shows interference. When the information is not erased, they do not. It is as if the photons knew what measurement would be made in their future and adjusted their past behavior accordingly. This does not mean information actually traveled backward in time in a way that could send messages or create paradoxes. Quantum mechanics is subtle. The interference pattern only becomes visible when you correlate measurements from different detectors, a process that requires information from both the past and future parts of the experiment. You cannot see the effect until after everything is complete. No signal can be sent faster than light or backward in time using this method. But the experiment reveals something deep. Quantum systems do not have definite properties until measured, and measurements can be correlated across time in ways that defy classical intuition. The past and future are entangled in quantum mechanics, connected in ways we are still working to understand. These experiments suggest that at the quantum level, time is not the simple forward flow we experience in daily life. Cause and effect become blurred, and the universe seems to operate according to rules that allow past and future to influence each other in constrained, consistent ways. Retrocausality in quantum mechanics suggests the future affects the past at quantum scales. Some interpretations of quantum mechanics take the delayed choice experiments and similar phenomena seriously as evidence for retrocausality, the idea that future events can influence past events. This is not time travel in the sense of sending information or objects backward, but it suggests that causality at the quantum level is not strictly forward. In standard quantum mechanics, the state of a system evolves forward in time according to the Schrödinger equation. But when a measurement is made, the system's wave function collapses, suddenly taking on a definite value. This collapse seems instantaneous and non-local, affecting entangled particles regardless of distance. Some physicists have proposed that instead of a forward-only process, quantum mechanics involves a kind of symmetry between past and future. Initial conditions at the beginning and final conditions at the end both influence what happens in between. This is called the two-state vector formalism, developed by Yakir Aharonov and others. In this view, a quantum system is described not just by its past state, but also by its future state, and both work together to determine present measurements. This sounds strange, but it makes predictions that match experiments, and it offers a different way to think about quantum mechanics. If retrocausality is real, even in this limited quantum sense, it has profound implications. It means the future is not entirely open, that some information about future measurements constrains present events. It does not allow for sending messages backward in time because the effects are statistical and only become clear in hindsight, but it challenges our notion of time's arrow. Most physicists remain cautious about retrocausality. Standard quantum mechanics, without invoking backward influence, explains all known experiments. Adding retrocausality may be unnecessary, an extra layer of interpretation that complicates without adding new predictions. But the debate continues, and experiments are being designed to test whether retrocausal models offer advantages over standard ones. At the quantum level, the nature of time remains one of the deepest mysteries, and we may need to rethink our assumptions about past, present, and future. Time travel experiments already done with particles and photons. While no one has sent a macroscopic object backward in time, experiments with particles and photons have explored time travel-like scenarios. These experiments use quantum systems to simulate closed time-like curves and test what would happen if time travel were possible at small scales. In 2010, researchers at the University of Queensland in Australia used quantum entanglement to simulate a photon traveling back in time and interacting with its past self. They created a setup where a photon's polarization state could influence a measurement that had already been made on another photon entangled with it. The results showed that the system naturally avoided paradoxes. The quantum state arranged itself in a self-consistent way, much like Novikov's self-consistency principle predicts for classical time travel. In another experiment, physicists simulated closed time-like curves using nuclear magnetic resonance techniques. They manipulated the quantum states of atomic nuclei to create conditions analogous to a particle traveling through a time loop. Again, the system behaved consistently. Paradoxes did not arise. The quantum evolution followed rules that ensured self-consistency. These experiments do not prove that macroscopic time travel is possible, but they show that quantum mechanics can accommodate time loops without breaking down. At small scales, the laws of physics seem to allow for time travel-like behavior, and nature handles it gracefully, avoiding contradictions through the inherent properties of quantum systems. This research is still in early stages, and interpretations vary. Some physicists see it as evidence that time travel might be possible, at least for information or quantum states. Others view it as exploring the mathematical structure of quantum mechanics without implying real-time travel. Either way, these experiments push the boundaries of what we thought possible and reveal that time at the quantum level is far stranger than everyday experience suggests. The arrow of time and entropy explain why we perceive time moving forward. Time seems to flow in one direction, from past to future. But the fundamental laws of physics are mostly time-symmetric. Newton's laws, Maxwell's equations for electromagnetism, even the equations of general relativity and quantum mechanics, they all work just as well if you reverse the direction of time. A video of planets orbiting a star looks perfectly normal, whether played forward or backward, at least from the perspective of the equations. So why does time feel like it has a direction? Why do we remember the past but not the future? The answer lies in thermodynamics, specifically the second law, which states that entropy, a measure of disorder or the number of possible microscopic states, always increases in a closed system. This gives time an arrow. The past is the direction of lower entropy. The future is the direction of higher entropy. When you crack an egg, it breaks and spreads. The reverse, an egg spontaneously assembling itself from scattered pieces, never happens. Not because it is forbidden by physics at the microscopic level, but because it is overwhelmingly improbable. There are vastly more ways for an egg to be broken than unbroken, so entropy increases. This asymmetry is not in the fundamental laws, but in the initial conditions of the universe. The Big Bang started the universe in an extremely low entropy state, highly ordered, and entropy has been increasing ever since. This increase creates the arrow of time we experience. Our memories are physical records, traces left by past events, and forming a record increases entropy. We remember the past because our brains store information about lower entropy states. We do not remember the future because it has higher entropy, and forming memories of it would require decreasing entropy, which does not happen spontaneously. If you traveled backward in time, you would be moving against the entropy gradient. What would that mean for your consciousness, which relies on entropy increasing to form thoughts and memories? This is one of the deep puzzles of time travel. The arrow of time seems fundamental to how we experience reality. Reversing it, even locally, might be incompatible with consciousness as we know it. Time symmetry in physics equations means most laws work backward and forward. Although we experience time as flowing forward, most of physics does not distinguish between past and future. If you take a video of particles colliding in a particle accelerator and play it backward, the backward version still obeys the laws of physics. Conservation of energy, momentum, and other quantities hold in both directions. Electromagnetism is time-symmetric. A light wave traveling forward in time is indistinguishable from one traveling backward, at least mathematically. General relativity is time-symmetric. The equations allow for both forward and backward evolution of spacetime. Even quantum mechanics, with its probabilistic nature, has time-symmetric equations in its fundamental form. The asymmetry we see in everyday life, the fact that we cannot unscramble an egg or watch smoke flow back into a cigarette, comes not from the laws themselves, but from statistical mechanics and the second law of thermodynamics. The universe started in a low entropy state, and the vast number of particles and interactions leads to an overwhelming probability that entropy will increase, creating the arrow of time. This time, symmetry at the fundamental level is why physicists take time travel seriously. If the equations do not forbid backward time travel, then it might be possible, at least in principle. The challenge is finding conditions where the symmetry can be exploited, where you can actually move backward through time without violating other constraints. Some interpretations of quantum mechanics break time symmetry. The collapse of the wave function, if it is a real physical process, happens instantaneously and is not time reversible. This has led some physicists to argue that time travel to the past is fundamentally impossible, because it would require reversing wave function collapse, which cannot be done. Others counter that collapse is not a fundamental process but an illusion created by decoherence and interaction with the environment, and the underlying quantum evolution remains time-symmetric. The debate continues. Time symmetry is a clue, a hint that the universe might allow time travel, but it is not proof. Turning the symmetry of equations into a functioning time machine is another matter entirely. Why we cannot change the past even if we reach it because of self-consistency. If you could travel to the past you arrive in is not separate from the past you came from. It is the same past, the history that led to you building a time machine and traveling. This means you were always part of that history. Whatever you do in the past, you already did it. There is no moment where history branches or changes. There is one timeline, and it includes your time travel. This is the principle of self-consistency, and it is a direct consequence of having a single, unchanging block of space-time. Suppose you travel back to yesterday and knock over a vase. When you lived through yesterday the first time, that vase was knocked over. Perhaps you did not notice, or perhaps you noticed but did not realize it was your future self who did it. The event was always part of history. You did not change anything. You fulfilled what always happened. This seems to limit your freedom. If you try to knock over a different vase, something prevents you. Maybe you slip, maybe you change your mind. Maybe the vase is bolted down. The universe enforces consistency. Your actions in the past are constrained to match the history you remember. Some find this philosophically troubling. It suggests a kind of predestination. If the past is fixed, and your actions in the past are constrained by consistency, do you really have free will? Or are you simply acting out a script that was always written? One response is that free will is an illusion anyway, whether or not time travel is involved. The laws of physics, deterministic or probabilistic, govern your brain's operation. Your choices arise from physical processes, not from some independent will floating outside causality. Time travel does not change this. It just makes the constraints more obvious. Another response is that you still make choices. You choose to knock over the vase. The fact that this choice was always a part of history does not make it any less your choice. The timeline includes your decisions, and those decisions are real, even if their outcomes were predetermined by the structure of space-time. Self-consistency is not a force or a mechanism. It is a logical requirement. Inconsistent timelines are not possible, not because something stops them, but because they are contradictions, like a square circle. They do not exist in the space of possible realities. Time travel, if it exists, operates within this constraint, allowing journeys to the past but not changes to the past. The block universe theory says past, present, and future exist simultaneously. Imagine time as a dimension, like space. Just as all locations in space exist simultaneously, even those far from you, all moments in time exist simultaneously in the four-dimensional structure of space-time. Your birth, your current moment reading this, and your death are all equally real, all existing at different coordinates along the time axis. This is the block universe view, also called eternalism. From a God's eye perspective outside space-time, the entire history of the universe is laid out, a vast four-dimensional object containing all events that ever were, are, or will be. You are not a three-dimensional being moving through time. You are a four-dimensional being, a world line. a thread stretching from your birth to your death through space-time. Your consciousness, your sense of now, is a moving point along that world line, experiencing one moment after another. The moments themselves do not come into being or pass away. They all exist. You simply move through them. This view fits naturally with relativity. The relativity of simultaneity shows that different observers disagree about which events are happening now. If now is relative, then there is no universal present moment. All events exist in the space-time block, and which ones you call past, present, or future depends on your motion and your location. The block universe solves some puzzles. It explains why time travel to the past does not create paradoxes. You are not changing the past because the past is a fixed part of the block. You are moving to a different location in the block, and whatever you do there is already part of the structure. But it creates other puzzles. If the future already exists, laid out in the block, is it not already determined? Do your choices matter if the outcome is already there, etched into spacetime? These are philosophical questions without clear answers. Some argue that determinism is true, and the block universe makes it obvious. Others argue that even in a block universe, your choices are real and meaningful. They are part of the causal structure that creates the block. You still experience uncertainty, still make decisions, still shape your part of the world line. The block exists, but you are one of the agents creating it. The block universe is not proven, but it is a compelling way to think about time, especially in the context of relativity. Time is a dimension. All moments exist. You travel through them one by one, and time travel would be moving through them in a different order. Your consciousness as a moving point through fixed space-time. If the block universe is real, what is consciousness? Why do you experience one moment at a time, rather than perceiving your entire world line at once? These questions lie at the intersection of physics, neuroscience, and philosophy, and we do not have complete answers. One possibility is that consciousness is fundamentally tied to the flow of information and the increase of entropy. Your brain processes information, creates memories, and anticipates the future. All of these are thermodynamic processes that increase entropy. Your sense of now, your feeling that time is passing, might be a byproduct of your brain operating in a universe where entropy increases. As your brain moves along its world line through the block, it processes information in sequence. Memories form, recording past states. Predictions form, anticipating future states. The result is the subjective experience of time flowing, even though from the block perspective, all moments are equally real and static. This is speculative, but it offers a way to reconcile the static block universe with the dynamic experience of consciousness. You are a pattern of information processing, and that pattern moves through space-time, creating the illusion of flow. If you traveled backward in time, what would happen to your consciousness? Would you experience time running backward, memories dissolving, thoughts unreeling in reverse? Or would your consciousness continue moving forward through its own internal time, even as you moved backward through external time? The physics does not answer this clearly. Some suggest that consciousness requires entropy to increase, so moving backward through external time might be incompatible with conscious experience. You might arrive in the past, but be unable to form thoughts or memories in the normal way. Others suggest that your internal thermodynamic arrow could remain forward even as external time runs backward, allowing you to think and act normally, while history rewinds around you. These are deep mysteries. Consciousness and time are both poorly understood, and their relationship is one of the most profound questions we face. Time travel forces us to confront these questions directly, to ask what it means to experience time, and whether that experience depends on the direction time flows. If time travel is possible, why have we not met time travelers yet? This question, sometimes called the temporal Fermi paradox, is a powerful argument against the possibility of backward time travel. If it is possible, and if civilizations in the future develop the technology, we might expect visitors from the future. Where are they? Several answers have been proposed. First, time travel to the past might simply be impossible. The equations of general relativity allow it under certain conditions, but those conditions might never be realized. Quantum gravity, the unknown theory that unifies relativity and quantum mechanics, might forbid closed time-like curves. The universe might have chronology protection, a built-in mechanism that prevents time machines from functioning. Second, time machines might only allow travel back to the moment the machine was created. If a wormhole time machine works by creating a time difference between two mouths, you can only travel back as far as the moment the mouths were separated. No one from the future can visit us because no time machine exists in our present. The first time machine will enable travel only within its operational future, not to times before its creation. This is a significant limitation, but it means time travel could become possible in the future without contradicting the absence of time travelers now. Third, time travelers might be here but undetected. If visitors from the future wish to remain hidden, they could do so. They might observe from a distance, use advanced technology to avoid detection, or visit in ways that leave no trace. They might have ethical guidelines against interfering with the past, choosing to watch but not interact. Fourth, time travel might be so difficult, dangerous, or resource-intensive that no civilization undertakes it casually. Even if possible, the energy requirements might be enormous, the risks substantial. Civilizations might build time machines but use them rarely, for specific purposes, and perhaps not to visit our particular place and time. Fifth, the many worlds interpretation might apply. If time travelers create new branches of the timeline when they visit the past, they never appear in the original branch. We do not see them because they go to alternate timelines, parallel versions of history, not ours. We are in the original branch, untouched by visitors from our own future. Sixth, we might be early. If the universe will exist for trillions of years, and if time travel becomes possible only far in the future, then we are living in the early epochs before time machines are common. The absence of time travelers is not surprising, because they do not exist yet and cannot travel back past the moment their machines are created. Each explanation has strengths and weaknesses. The absence of time travelers is suggestive, but not definitive. It is evidence that backward time travel, if possible, is at least rare, difficult, and constrained. It is not proof of impossibility, but it is a datum that any theory of time travel must account for. Practical future time travel might involve sending information, not matter. Even if transporting people through time proves impossible, sending information backward might be achievable. Information is physical, encoded in the states of particles or fields, but it does not require massive infrastructure. A microscopic wormhole, a brief quantum fluctuation, or a carefully engineered quantum system might allow transmission of data without the enormous energy needed to send a spacecraft. Imagine a wormhole the size of an atom, held open for a fraction of a second by exotic matter or quantum effects. You could not fit a person through it, but you could send a radio signal, a stream of photons encoding information. If this wormhole connects two different times, it becomes a communication channel to the past or future. The engineering challenges are still immense, but they are smaller than for macroscopic time travel. The amounts of exotic matter needed scale with the wormhole's size, so a tiny wormhole might be feasible even if a human-sized one is not. Quantum systems offer another potential route. Some proposals involve using entangled particles and post-selection to send information backward. These are highly speculative and controversial, with many physicists skeptical that they could work without violating causality. But research continues, exploring the boundaries of what quantum mechanics allows. If information can be sent backward, even in limited ways, it still raises paradoxes. You could receive a message from your future self instructing you not to send the message, creating a contradiction. Self-consistency would apply. Perhaps any message you receive is one you are destined to send, creating a loop but no paradox. Or perhaps receiving a message from the future collapses possibilities, forcing a particular timeline to occur. The implications of even limited backward information transfer are profound. It could allow precognition, knowledge of future events before they occur. It could enable communication with the future, sending questions and receiving answers from more advanced times. It could also be used to create computational shortcuts, solving problems by sending answers backward from a future where they have been computed. These are speculative ideas at the frontier of physics. But if any form of time travel becomes practical, sending information might be the first step, a narrow channel through time that expands our understanding and capabilities. How close we actually are to time travel technology. For forward time travel, we are remarkably close, at least in principle. The physics is well understood. Time dilation is real, proven, and used in technology like GPS. We know how to travel into Earth's future. Build a spacecraft capable of reaching a significant fraction of light speed, accelerate, travel for a period, and return. You will have aged less than people on Earth. You will have traveled into their future. The barrier is not physics, but engineering. We do not have propulsion systems capable of reaching relativistic speeds. Our fastest spacecraft, the Parker Solar Probe, reaches about 192 kilometers per second, less than 0.1% of light speed. To reach 90% light speed would require propulsion technology far beyond anything we have. Fusion rockets, antimatter engines, laser propulsion. These are theoretical possibilities, but none are close to practical implementation. Even if we solve propulsion, the energy requirements are staggering, likely requiring resources on the scale of planetary or solar system-wide infrastructure. So, forward time travel is possible in principle, but likely centuries away in practice, unless we make unexpected breakthroughs in energy generation and propulsion. For backward time travel, the situation is far less clear. We do not know if it is possible at all. The theoretical mechanisms, wormholes, rotating black holes, cosmic strings, all require conditions we have never observed and may not be able to create. Exotic matter with negative energy density is needed, and we do not know if it can be produced in sufficient quantities. Even if the physics allows backward time travel, the engineering might be forever beyond reach. Some physicists estimate that building a wormhole time machine would require the energy output of an entire star or galaxy. Such projects might be possible for advanced civilizations millions or billions of years ahead of us, but not for humanity in any foreseeable future. Quantum time travel for information is closer, perhaps achievable in decades or centuries if the concept is sound. Experiments are ongoing and our understanding is growing. But we are still in the early stages, not yet sure if the ideas will pan out. The honest answer is that for practical time travel, especially backward, we do not know how close we are. It might be a few centuries away, it might be impossible, or it might require technologies and understandings we have not even conceived. Time will tell, which is perhaps appropriate for a technology about traveling through time. The philosophical implications of time travel challenge free will and determinism. Time travel, especially to the past, forces us to confront deep philosophical questions. If you can travel to the past and your actions there are constrained by self-consistency, do you have free will? Or is everything predetermined, a script you must follow? This is an ancient debate, but time travel gives it new urgency. In a block universe where all moments exist and the past cannot be changed, it seems that the future is fixed. Your choices are already part of the structure of space-time. You cannot do otherwise than you will do. This sounds like determinism, the idea that all events are determined by prior causes, and free will is an illusion. But even without time travel, determinism is a question in physics. If the laws of nature govern everything, including your brain, then your decisions are the result of physical processes. Quantum mechanics adds randomness, but random is not the same as free. You do not control quantum outcomes any more than you control deterministic ones. Time travel makes the issue vivid. If you travel to the past and try to kill your grandfather, you fail. Something always stops you. It feels like an external force constraining you, removing your freedom. But perhaps the constraint is internal. Perhaps you, for whatever reasons arising from your brain state, your memories, your personality, simply do not succeed. The failure is still your action, still your choice, even if the outcome was predetermined by the need for consistency. Some philosophers argue that free will is compatible with determinism. You are free if your actions arise from your desires, beliefs, and reasoning, even if those mental states are themselves determined by prior causes. Time travel does not change this. You still act according to your will. The fact that the consequences were always going to happen does not make your will any less real. Others argue that true free will requires the ability to do otherwise, and time travel seems to remove that. If you are destined to fail at killing your grandfather, you cannot do otherwise, and thus you are not free. These debates have no easy resolution. Time travel, like many topics in physics, pushes philosophy to its limits, forcing us to question assumptions we usually take for granted. What time travel would mean for humanity's understanding of reality? If time travel to the past becomes possible, it would revolutionize our understanding of the universe. It would confirm that time is not a simple forward flow, but a dimension we can navigate, at least under certain conditions. It would validate aspects of general relativity in dramatic fashion, showing that spacetime can be curved and twisted in ways that allow loops and journeys to earlier eras. The practical implications would be enormous. Communication with the past could allow us to warn of disasters, to send knowledge backward, to shape history. Though self-consistency would constrain what could be changed, Even limited influence could be valuable. Receiving messages from the future could provide insights, solutions to problems, warnings of dangers. The ability to explore history directly, not through archaeology and records but by visiting, would transform our understanding of the past. We could witness events, resolve historical mysteries, see how civilizations rose and fell. The philosophical implications would be profound. Time travel would challenge our notions of causality, free will, and the nature of existence. It would force us to accept that the past, present, and future are all equally real, all part of a unified spacetime structure. Our place in the universe would feel different, knowing that time is not a river carrying us forward, but a landscape we might someday learn to traverse. Even if backward time travel proves impossible, the attempt to understand it pushes science forward. Exploring the limits of general relativity, probing the connections between quantum mechanics and gravity, investigating exotic matter and energy, all of these are valuable pursuits. They deepen our knowledge and may lead to discoveries we cannot yet imagine. Time travel sits at the boundary of the possible, a concept that might be realized or might be forever out of reach. Either way, the journey to understand it is worth taking. It reveals the universe's strangeness, its beauty, its profound mysteries, and it reminds us that we live in a cosmos far richer than everyday experience suggests, a place where time itself might one day bend to our will. The comfort in uncertainty and living in an era where anything is possible. We live in a remarkable time. We understand enough physics to know that time travel is not obviously impossible. The equations allow it under certain conditions. Yet, we do not know if those conditions can be realized. The future is open, uncertain, full of possibilities. This uncertainty is not a weakness. It is a gift. We stand on the edge of knowledge, looking into the unknown. Time travel might be achieved in a century, in a millennium, or never. We do not know, and that not knowing is part of the wonder. The universe still holds secrets. There are questions we cannot yet answer, phenomena we have not yet observed, technologies we have not yet imagined. Time travel is one of these frontiers, a place where our theories hint at possibilities but do not guarantee them. In this moment, in this era, we can dream. We can explore, theorize, experiment, push the boundaries. We can ask what if and follow the mathematics wherever it leads. The future is not written, at least not in a way we can read. Even if it exists in the block universe, laid out and unchanging, we do not know its contents. From our perspective, moving forward through time one moment at a time, the future is a mystery. Time travel would not change that. Even if you could visit the future, you would only see one possible path, one outcome among many, or one branch of the timeline if many worlds is true. Uncertainty would remain. The universe would still surprise you. As you rest tonight, consider that you are part of a story that is still being written. The atoms in your body are billions of years old, forged in stars and scattered across space. They have traveled from the Big Bang to this moment, crossing vast distances and immense times, and they will continue forward, becoming part of new structures, new forms, long after your consciousness has ceased. Time carries us all, gently and inevitably. We move forward through it, one heartbeat at a time, one breath at a time. We cannot stop it or reverse it, at least not yet, but we can marvel at it, study it, wonder at its mysteries. Time is the stage on which all events unfold, the dimension that separates cause from effect. the flow that gives structure to experience. And perhaps one day it will be a landscape we can explore, a territory we can map and navigate. Until then, we travel forward, together, through the night and into an uncertain but fascinating future. Closing thoughts on time as the ultimate mystery we are part of. Time is perhaps the deepest mystery in all of physics. We experience it constantly, every moment of our lives, yet we do not understand it. Why does it flow? Why can we remember the past but not the future? Why does it have a direction? What is the now? And why do we perceive it as special when relativity tells us it is not universal? Time travel, whether possible or not, forces us to confront these questions. It takes something we thought we understood, the simple forward passage of moments, and reveals layers of complexity beneath. Time is woven into the fabric of spacetime, curved by mass and energy, flowing at different rates in different places. It is flexible, malleable, strange, and we are part of it. You are not separate from time, observing it from outside. You are embedded in it, a pattern of atoms and energy moving through the fourth dimension, experiencing it from within. Your world line stretches from your birth to your death, a thread in the vast tapestry of space-time. Every thought you have, every action you take is a point on that thread, a moment in your journey through time. Time travel, if it exists, would allow unusual paths through space-time, loops and curves and backward journeys. But even without time travel, the journey is remarkable. You are moving through a dimension, experiencing it unfold, participating in the cosmic story. The past is behind you, the future ahead, and the present is this moment, this breath, this quiet stillness as you drift toward sleep. Time does not stop, but it can slow. It can soften. As you relax, as your breathing deepens and your thoughts quiet, time seems to stretch, each moment lasting longer. This is not time dilation in the relativistic sense, but it is real in its own way. The subjective experience of time, the pace at which it seems to flow, is part of the mystery too. We do not understand consciousness, and we do not understand time, and the intersection of the two is perhaps the most profound question we can ask. Tonight, as you rest, you are traveling through time at 1 second per second. Tomorrow, you will be 1 day in the future. In a year, you will be a year ahead. This is time travel, the ordinary kind, the kind we all do without thinking. But it is no less remarkable for being common. You are moving forward through the universe, part of its unfolding, part of its story. And somewhere, in the equations and the theories, in the mathematics and the experiments, we are slowly learning that time is stranger, richer, and more wondrous than we ever imagined. The universe's timeline continues while you rest. Even as you lie here, drifting toward sleep, the universe continues its ancient dance. Stars burn, light travels, particles decay, galaxies rotate, black holes accrete matter, cosmic expansion stretches space itself. Time flows on, impartial and constant, or perhaps flowing at different rates in different places, depending on gravity and motion. Somewhere, a photon is racing through empty space, crossing light years in what feels to it like no time at all. Somewhere, a particle near a black hole's event horizon is experiencing time so slowly that seconds for it are years for distant observers. Somewhere, perhaps, a future civilization is manipulating space-time, bending it, exploring its possibilities, reaching back toward us through the dimension we call time. Or perhaps not. Perhaps we are alone in time as we are in space, the only travelers, moving forward 1 moment at a time, unable to deviate from the path. The universe does not tell us its secrets easily. We must work for them, experiment, observe, calculate, imagine. And even then, some mysteries remain. Time may be one of them. A riddle we can approach but never fully solve. Or it may be that one day, centuries or millennia from now, humanity or our descendants will understand time completely. They will see it as we see space, a dimension to be traveled, mapped, and explored. They will journey through it, visiting past and future, witnessing the birth of stars and the death of galaxies. They will exist across time as we exist across space, four-dimensional beings fully aware of their extent through the fourth dimension. That future, if it comes, is far away. But the seeds of it are planted now, in the equations, in the experiments, in the wondering and the questioning. Every mystery solved brings us closer. Every question asked deepens our understanding. Time itself is patient. It has carried the universe for nearly 14 billion years. It will carry it for trillions more. In that vast span, our moment is brief, a flicker, a single breath. But it is our breath. It is our moment. And in it, we can wonder, we can dream, and we can rest. Your place in the arrow of time moving gently forward through sleep. You are part of time's arrow, the flow from past to future, the increase of entropy that gives direction to events. As you sleep, your body continues its processes. Cells repair, memories consolidate, energy is consumed and dispersed. Entropy increases, as it always does, as it must. This is the arrow of time, the reason you remember yesterday but not tomorrow, the reason eggs break and do not unbreak, the reason the universe evolves from order toward disorder. And yet within this flow, complexity arises. You are a temporary eddy in the stream, a local decrease in entropy maintained by consuming energy from your surroundings. You are ordered, structured, alive, all because the sun pours energy onto Earth, and that energy flows through ecosystems, through food, through your body, and eventually radiates away as heat. This flow sustains you, and it carries you forward through time. Sleep is part of the cycle. Rest, repair, renewal. Your brain processes the day's experiences, consolidating memories, clearing metabolic waste, preparing for tomorrow. This is time's work, the forward progression, the building of past from present. When you wake, you will remember tonight, this moment of drifting, this journey through thoughts of time and space. The memory will be part of you, encoded in neural connections, a trace of the past carried into the future. Time moves forward, and you move with it. Not fighting, not resisting, but flowing, gently like a leaf on a river. The current is strong, the direction unchanging, but the journey is yours. Every moment is unique, unrepeatable, a point on your world line that exists only once in all of space-time. This moment, right now, will never come again. It will become part of the past, a memory, a fixed point in the structure of space-time. And the future, unknown and uncertain, approaches. One moment at a time, one breath at a time, carrying you forward into tomorrow, into next week, into the years ahead. You cannot see what is coming, but you can trust that time will carry you there, as it has carried everything since the beginning. Good night message and peaceful send off into the cosmic mystery. And now, as the stars wheel overhead and the universe continues its vast, slow turning, it is time to let go. Let go of questions, of wondering, of thinking. Let your mind settle like dust after a storm, soft and quiet. Time will continue without your attention. The cosmos does not need you to watch over it. It has endured for billions of years, and it will endure for billions more. Tonight, you can rest. You have traveled through ideas, through theories, through the strange and beautiful mathematics of time itself. You have glimpsed possibilities, wormholes and black holes, particles and paradoxes, the past and the future woven together in ways both elegant and mysterious. You have considered your place in the universe, a small warmth in the dark, a brief flicker of consciousness in the vast span of time. And that is enough. It is more than enough. You are part of something immense, something ancient and ongoing. The atoms in your body are stardust, remnants of exploded suns. The time you experience is the same time that has carried galaxies into existence and will carry them into darkness. You are connected, interwoven, a thread in the fabric of spacetime. As you drift now toward sleep, imagine time softening around you, the rigid ticking of clocks fading, the press of past and future dissolving. There is only this moment, this breath, this gentle descent into rest. Time will be here when you wake. The mysteries will remain. The questions will wait. But tonight, let them go. Float, weightless, through the dark. Let the universe hold you. You are safe here, in this moment, in this place, moving gently forward through time, as everything does, as everything must. If you are still awake, you can watch the next chapter now. But if sleep has found you, then rest well. Dream softly, and know that time, patient and eternal, will carry you safely through the night. Good night.